Whose life would be better if you knew more C++? Whose life would be better if your coworkers knew more C++? Let's get started.
Good morning, everyone, and thank you for coming. My name is Bob Steagall, and I have the privilege of giving some talks in this year's Back to Basics track. Each session in the track is about a single concrete topic like this one, which is about debugging techniques. And our goal is to produce content for that track that covers important things you need to know as a working C++ programmer. As usual, I'd like to thank our Back to Basics track chair, Arthur O'Dwyer, and also John Kalb for running the conference. This introductory talk is aimed towards newcomers and those with perhaps less C++ experience. I hope that to provide a basic set of debugging tips and tools and tricks that you can apply to your own daily work. And for those of you with more experience, hopefully there'll be something you'll find useful here. There's not actually any code at all in this. Instead, it's a discussion of ways of approaching the problem of debugging. So I've shown these slides before, but I think it's important to remind ourselves of the cost of software failures and how important it is to write correct software and how critical the process of debugging is. So in January 2018, Tricentis published a document of documenting 606 important software failures in calendar year 2017. And the failures affected nearly half the population of the Earth and were responsible for almost $2 trillion of lost revenue. In May 2020, 3 years later, Undo Software and Judge Business School at Cambridge in an MBA project published some work which indicated that reproducing and fixing a failure takes about 13 hours on average. And more than a quarter of the time on average that developers spend doing work is spent reproducing and fixing bugs. And over the course of this study, they determined that about 620 million developer hours per year are spent on this problem at a cost of a little over $60 billion in salary paid and over $1 trillion of enterprise value lost. It's a huge amount of money and a huge amount of time. And so if we can find ways to reduce that cost, it benefits everyone. I've also shown this slide before. I won't linger on it too much, but the cost of software failures has direct and sometimes tragic impact on people. In the 80s, there was a device called the Therac 24, which was produced by Atomic Energy of Canada. It was a radiation therapy machine. Due to some design defects in the hardware and several software defects that were catastrophic, it was possible in certain situations for people to receive a dose of radiation that was hundreds of times greater than it should have been. 6 people were dosed and 3 people died. In 1996, 37 seconds after launch, the Ariane 5 launch, the rocket blew up. And the reason is that there was a double to int16 conversion. The double was keeping track of a parameter that accumulated continuously during flight, and for some unexplainable reason, was storing that value, converting it to an int16. Well, guess what? When the value got greater than 32,767, it wrapped around, and the value in the double suddenly was nonsensical, and the value in the int16 became nonsensical, which was controlling a flight control thing, and it caused the rocket to vibrate and blow up. And it cost $370 million. Later, in 1999, the Mars Climate Orbiter burned up in space, and this was purely because of an incorrect imperial or English units to metric conversion. $235 million and many years of effort lost because of a silly, stupid software error. In August 2012, more recently, Knight Capital, Wall Street automated trading firm, lost $460 million in 45 minutes and went out of business. And this is because they allowed in production code, they had a production build that had a test flag which shouldn't have been there. And the purpose of that test flag was to automatically execute a set of test trades to validate the software. Well, guess what happened? When it was in production, it did what it was supposed to do, and it triggered 4 million order executions in 45 minutes, and it disrupted the prices of 154 stocks on the New York Stock Exchange and ended up driving them out of business. A lot of people lost a lot of money. More recently than that, of course, tragically, 2 Boeing 737 MAX jets crashed, killed a total of 346 people. And Boeing relied on a system called the Maneuvering Characteristics Augmentation System, or MCAS. And if you are a member of IEEE, the April 2019 IEEE Spectrum had an article written by a guy named Gregory Travis, who is a pilot, and he describes in layman's terms the systems that failed. There's a lot of information in that article, but he summarizes the failure in 3 main points. Number 1, Boeing produced a dynamically unstable airframe, the 737 MAX. Boeing then tried to mask the dynamic instability with a software system that would correct that instability in real time. And finally, the software relied on hardware systems that were known for their propensity to fail, the angle of attack indicators. And they didn't include in their software the ability to do any sort of cross-checking the output of those indicators against other sensors on the airplane, or even the other angle of attack sensor on the other side of the airframe. So yes, there was a combination of aerodynamic design and hardware design and software design issues, but at least with respect to the software design issues, these are things that should have been caught sooner and contributed. They weren't the only thing, but they contributed to the problem. So if you go to my talks, you know I like to begin with definitions, and I'd like to talk about what bugs are and what debugging is. That's the point of this session. I'll talk about some challenges that we face when we try to debug problems, and I will put forth a simple process for debugging, one that I've found useful over the years, and I'll end with some recommendations about how to approach the problem of debugging in your own world. And as I said, I hope that you'll find some useful tips there, or maybe you can print out some of the ideas and keep them beside you when you're trying to solve some of these problems. So I have some opinions here, so please don't be offended by them. And since I'm up here, my opinions will be the right one for the next hour. So what are defects or bugs? Well, the most common view of what a defect or a bug is that it's an error in a program that causes it to behave in some way that we don't expect. We think it's incorrect or unintended or unexpected. And that's probably the most common way that people think about it, right? But I propose that there's a different and a better way of thinking about it, or at least it's the way I think about it. And since I'm up here, it is a better way. If you think about it, at the end of the day, each software system is subject to a set of requirements that describe its environment, its inputs, its usage, its inputs, its outputs, its expected behavior. And these requirements are not always explicitly stated, but they're always present. We always have expectations of how a software system should behave with the outside world in terms of processing input and sending output. So they're always there. And one way of thinking about defects, the way I think about it, is a software defect is a nonconformity to those requirements. Some subset of the system's requirements are being violated. As C++ programmers, we think about this as precondition violations or postcondition violations or invariant violations. So whichever way you think about it, we are violating some requirement that's been stated implicitly or explicitly. And if you ever happen to work in a regulated industry like medical devices, medical imaging, nuclear, aerospace, automotive, this is a very common viewpoint in those industries, and it's one that I think we should actually all adopt because it is useful to think about things in this way. So what then is debugging? Well, Wikipedia, which is the wellspring of all human knowledge, says that debugging is the process of finding and resolving bugs, defects, or problems that prevent correct operation within our programs, software, or systems. And, you know, that's about as good of a definition as you can find. And it is Wikipedia, so it is, you know, must be true. So, however, this makes some assumptions. The first assumption is that we know what correct operation is, and we also know what incorrect operation is. And in a sense, those are two different things. Just because you know what correct operation is doesn't necessarily know what incorrect operation is, and vice versa. That we have the ability to observe the programs and or their outputs so that we can understand this behavior that we think might be incorrect. That we have the ability to change the underlying source code or the program data so that we can fix the problem eventually. That we have the ability to build and test those updated programs that we think will fix the problem. And yes, it's trivial to say these things, but I think sometimes it's very useful to state the obvious to make sure that everyone understands what that is. So, a nonconformity then is a failure to meet one or more requirements. And if you've ever studied any ISO quality systems or IEEE or IEC quality based literature, it's a very common definition. And I'm going to call it defect instead of bug. So a defect is incorrect program data or code or settings or dependencies that cause a nonconformity. It could be that the program is working correctly, but the configuration that you've sent it with has a bug in the configuration, right? All of these things can be thought of as defects. A symptom, I'm going to use this term to mean an observable evidence of a defect. Symptoms are what you observe. A deterministic defect is a defect that doesn't change its symptoms under a well-defined set of conditions. In other words, given the same input and the same conditions, if you run the program, every time you run the program, you'll observe exactly the same symptom, right? The thing we all dread, however, is the non-deterministic defect, which is one that changes its symptoms from run to run under a well-defined set of conditions. You run the same program with the same input on the same system over and over again, and you get different results each time. These are the ones that make our life difficult and cause gray hair and loss of sleep. Now, you've probably heard non-deterministic defects. They're sometimes playfully called Heisenbugs, which is on the Heisenberg uncertainty principle, named after the German physicist Werner Heisenberg. And of course, there's the corresponding Bohr bug, which was named after Danish physicist Niels Bohr, and it's a play on his original deterministic model of atoms. So if someone says Heisenbug or Bohr bug, now you know what they mean. I'm going to define the word context for this presentation to mean the totality of the environment in which a program that's exhibiting some symptoms is running. It's everything in the environment that contributes to how that system is acting. And a problem report is some information that describes one or more symptoms in that context. I'm going to define analogous context to mean one that replicates enough of the original context so that you can reproduce a set of symptoms. I'm going to define the lab as being a setting in which you, as the programmer, have total control over the context. And I'm going to define the field as the setting where you have no control over the context, right? It's your user or your tester or somebody else. So, a problem report describes one or more symptoms in some context. Each symptom, we think, is caused by one or more defects. And evidence of a defect is made observable by one or more symptoms. So, here's a little multiplicity diagram that sort of, in my mind at least, shows the relationship between a problem report, symptoms, and defects. There's not necessarily a one-to-one correlation between symptoms and defects. A given symptom can be a result of multiple defects. A single defect can cause multiple symptoms. So when we are debugging, there are a number of challenges that confront us, right? Our problem reports may be, and I will be generous here, unhelpful, right? They can be misleading, they can be inadequate, they can have incorrect description of the symptoms. I once got a bug report for a library that I published that said, yeah, we're getting an error when, we're copying two instances of your string. I said, can you be more specific? And they said, no. And that was because I had sold it to somebody that was doing some DoD work and they couldn't talk about it. So based on that, I had to try and figure out what was wrong. Oftentimes, users will not have much knowledge about the product and they will tell you the incorrect version or configuration or the platform. So, it can be a challenge getting correct and useful information from the people that are creating the problem report. Problem reports don't always indicate the actual problem, and sometimes unexpected behavior could be due to a lack of knowledge on the user's part, and it's not always a defect. Or unexpected behavior could actually be correct behavior, at least according to if it meets the requirements, right? It could be, a program could be creating some output that no one expects, but when you think about it, or you go back and look, it's like, all right, here's a corner case we never considered. The program's actually working correctly, we just never thought about this corner case, right? It's not necessarily a defect. Collecting program state data can be really challenging at times. Sometimes users can't or won't provide you the log data or the settings or crash data, things like core files. And so the information that you receive in this regard could be, incomplete, inconclusive, unavailable, non-existent. Symptoms may not indicate the cause. The cause and the effect, importantly here, especially in the case of non-deterministic bugs, is that the cause and the effect may be distant from each other in space and in time. And by space, I mean in terms of lines of code, right? The cause of a problem may be in some file that is hundreds of files away from where evidence of the symptom was first observed. It also could be in time. It could be that a problem is caused, an invalid state is generated in the executing program at time t0, and it's not actually observed until some time t1 that's much later, right? So there's potentially a huge distance in time and space between the cause and the effect. Defects and symptoms can sometimes be correlated in the sense that if you think that you found the problem and you're actually repairing the problem, during the process of executing the repair, the symptoms change, right? And then when that happens, you have to go and look at the new symptom and say, well, is this new symptom that I've observed as I've attempted to fix the problem indicative of something else that's wrong, right? It's not just like repairing a symptom fixes the defect, the symptoms can change. And of course, we always try to avoid this, the case where if you fix one defect, you introduce new problems, right? And this is indicative of old code, messy designs. It's indicative of flaws in the underlying program itself. And that's a tough situation to deal with. And the best thing you can do, I think, in that case is make the footprint of the fix as small as possible so that you don't disrupt the rest of the spaghetti on the plate. And of course, the worst challenge that we face is that symptoms are often difficult to reproduce. You can't always go to the field and debug problems. And constructing an analogous context in your lab setting is not always feasible or even possible. Program input is not always available. If you've shipped some software and your user is saying, well, when I run it with this particular input, the program fails or I get this error, and you say, can you provide me with that input? And they say, no. Can you narrow it down to some input that fails rather than all of your input? And they will say, no. So you have to try and infer, based on their description, what input is causing it to fail, right? Symptoms from non-deterministic problems are especially challenging. So, in theory, the process of debugging is one in which you You try to characterize and reproduce the problem. You determine the surrounding context, and you try to observe this allegedly incorrect behavior for yourself. You try to find the lines of code in the product which you think are responsible for that defect. And then you try to classify that defect. You need to understand what kind of defect is this? Is it a design flaw? Is it a logical flaw? Is it a configuration management flaw? There's all kinds of different categories of bad things. And it's very helpful to figure out which category of bad thing your observable symptoms and your defect fit into. And then, of course, trying to understand. You need to determine the cause of the defect and its relationship to the whole thing, right? Because you want to make sure if you need to understand that relationship so that when you fix it, you don't disrupt the rest of the whole. And then finally, repair. You want to repair the defect without breaking anything else. So we tend to think of debugging as a simple linear process, right? And so let's pretend I'm writing a function that describes the process. So my job is to do some debugging. The input is a product and a problem report. And so I try to characterize and reproduce that problem. I try to locate that problem. I try to classify that problem, right? Try to understand it. Then I create a new version of the product where I think I fixed it, and then I return that, right? Life is good. Well, the reality is that life is not really that simple. The process, as described, appears to make sense, and for simple problems, it probably will work. But in theory, there's no difference between theory and practice, while in practice, there usually is. I love this quote. It's been famously misattributed to a number of very smart people, but it actually, as far as I can tell, first appeared in the Yale Literary Magazine in 1882. It's been around a long time. So I think there's an analogy here with the debugging process and software engineering processes. And one is actually a subset of the other. So you're probably familiar with the simple waterfall process, right? This is an analogy to the simple debugging process, and it works in simple cases. You can work through the steps in a linear fashion and derive some satisfactory result at the end. But most of the time, it's insufficient to accomplish the task. And so this is a software engineering process that I like very much called the rational unified process, and I'm using it here as an analogy for the debugging process. You have actually a number of things that go on concurrently, which is represented by the different lines there, and you have different phases or iterations that you go through, which are represented by the horizontal axis. And debugging is very much like this. There are a number of things that you have to do concurrently, and you end up doing them iteratively until you get to what is hopefully a satisfactory result at the end. So going back to code, if I had to write the debugging process the way I do it at least, first thing you do is you look at the problem report, you review it, try to understand what's being said in that report. And my advice in this regard is don't brush it off. Try to read between the lines. Try to really understand what's being said and ask for clarification if you don't understand what's being said. Because oftentimes the users in their domain don't necessarily understand the language that you understand in your domain. Then we move on to characterize and reproducing the problem. And then what I try to do is create a clone of the thing that I think is working incorrectly. And, by clone here, I don't mean like a Git clone, although certainly you could do that. Create a new branch, a new repo, whatever. But it's a conceptual cloning. I want to duplicate the software, the source code of the thing that I think is failing, and I want to put it in a sandbox so that I can examine it without affecting anything else. And being able to, it's an essential part of being able to duplicate the problem. So then I would iterate. So assuming that I can reproduce the problem and also assuming that management has said, yeah, we want you to fix the problem, we'll give you some time and money to do it, right? Well, then I try to understand, locate, and classify the problem simultaneously. And I've try to indicate that by asynchronously launching some threads here. And the idea is that understanding, locating, and classifying the problem, these are not totally orthogonal things. There's feedback amongst them, even though I'm separating them out for the purposes of this conversation. These are really three things that you're doing all of the time while you're trying to debug a problem. And so at some point, I will come to believe that I've gained some insight, which honestly doesn't happen that often. I will know where I think the problem is, and I will have a tentative category for what how I will categorize this problem. And then I will attempt to repair. Many times this will be unsuccessful, and I'll go through the loop again. However, at some point, either I will have fixed the problem, or management will say, that's enough. And assuming that I fixed it, I will deliver the next version of the product. And if not, or if management is unhappy, then I might have to update my resume. Okay, so let's talk about characterizing and reproducing the problem. So I think of characterization as being determining the context, and context in sense of the word that I defined earlier, in which the symptoms were observed. And this is this information and more: version number, platform, resources, external interfaces, configuration data, everything you can find out about what was going on in the environment where the problem occurred. Every bit of information that you can find that would allow you to, in your lab, instantiate an analogous context so you could try and reproduce the problem. And of course, reproducing the problem means in your analogous context, in the lab, or in the field if you're lucky, running enough of the program or enough of the system so that you, for yourself, can observe the symptoms that have been reported to you. And a major part of this could be developing or updating existing test assets, unit tests or system tests or test plans, to conclusively and reproducibly demonstrate the failure that you think is occurring. And pro tip here, make sure you're looking at the correct source code. I worked with an engineer once, and it's kind of a funny story, but he had two repos, same software, and he had two X-terms open, one to each repo. And he was changing code and compiling in one X-term. And then he would run it in the other one and didn't realize he was doing it. And he spent hours changing code, and it wasn't fixing the problem. So, word to the wise. So, characterizing and reproducing a problem is vital to the debugging process. It's almost impossible, or at least it's extremely difficult, if you can't do this. So let's think about understanding, locating, and classifying the problem. So understanding the problem. In my mind, understanding means gaining enough knowledge about the problem and the context in which it occurs that you think you can make changes to carry out a repair. Doesn't guarantee that you actually will, but it's an iterative process. You come to understand what the problem is, the environment in which the problem's occurring, the environment in the code, and the surrounding state of the code and the program when it's executing. So at a minimum, you should think at least that you've located the incorrect lines of code, determined why the code is incorrect, not just that it is incorrect, but why is it incorrect. Determined what you think is the classification or the category of the problem, and formulated in your mind or on paper or the whiteboard some set of proposed changes to the code that you think is going to fix the problem. And importantly, determined how your proposed changes would affect the runtime state of the code, right? Just because you think you fixed it, you're changing it is in effect a cause. Do you understand the effect that comes after that? And determine whether or not your proposed changes would correct the problem. So, my advice is to try and inspect and also you need to inspect and verify the associated test assets, right? It could be that your test cases or your test harnesses or unit test or something is incorrect there in your testing. And perhaps your testing is revealing a problem that doesn't actually exist because the test itself is flawed. So, however, if that's not the case, then you should have test data or test assets that demonstrate both correct and incorrect behavior. Keep in mind that the defect may not be where you expect it is. And keep an open mind and be ready to question all parts of the program. Just because you think the defect is in Module A doesn't mean it's not actually in Module J or some other place. So keep an open mind. It's important. And another way of thinking about it, and one that can be useful when you think you're stuck, is ask yourself, where is the defect not? Can you definitively rule out sections of code or sections of the program where you absolutely know the defect is not there? If you can do that, that's less you have to think about, right? And sometimes if you say, well, I think the defect is not in Module A, but then you try to prove that the defect is not in Module A, sometimes the very act of trying to prove the absence of a defect can reveal where it really is, right? And you can always go the bobblehead route, right? Try to explain to yourself or someone else why there's a defect and why your proposed fix will resolve it. And of course, I'll do a favor to John here and say we have the bobbleheads on sale here at CppCon. So try to explain your problem to the bobblehead. And just verbalizing can oftentimes help you gain understanding. Locating the problem, and this is probably the hardest of the three things. Well, first of all, if you can, and you can't always do this, employ good development practices at the outset, right? Sometimes you're handed a plate of spaghetti and there's nothing you can do. But if you have some control over the situation, try to employ good modular development. Use an iterative and incremental bottom-up development process. You test often after each new bit of code, and that way if there's an error, it's probably in the last section of code that you wrote. So add functionality in small sections. And as you're creating new things, add test assets for each new increment of functionality. You build the program incrementally, add your test assets incrementally, so that every step along the way, you can be sure that you're building on something solid underneath. When you change things, when you add new code, verify that the new code doesn't cause previous tests to fail, right? Sounds obvious, common sense, but you'd be surprised how often people don't do this. You've probably observed it in your own organizations. And verify that the new code passes its own test cases. I once worked in a company, and I was sat right across the hall from a very senior engineer, and we were working on two platforms, Linux and FreeBSD. And he was a really smart guy and did a lot of optimization and did it all on Linux. Would check it in the main branch, and things would go off, and the automated test would run, and it would fail on FreeBSD. And guess who got to fix his problems? This guy. Because there were platform differences between Linux and FreeBSD at the time. Of course, I was not in a position to say, Kevin, you really need to check this. Practice defensive programming. You all know what defensive driving is. Assume that every driver on the road is out to get you. Well, you should assume that the code is out to get you and everybody else in the world is out to get you. And if you adopt that attitude, you're less likely to create problems. So it's much easier to find defects in code that's well designed and that's well written and it has extensive test assets. And preferably the whole product does this. At a minimum, your fixes should. Sometimes, as I said, you're handed a plate of spaghetti, it's a mess, there's nothing you can do about it, but at least in your tiny little chunk of that universe where you're fixing a problem, you can be disciplined. And so my advice is try to do that. Use trace logging. So I'm going to go into some specific, little lower level specific techniques. So trace logging, right? It's generating output that describes the program state as it executes. In simple cases, you can instrument your code with print statements. In more complex systems, there's probably logging facilities that are built in. So you can turn up the log level or introduce new logging statements and effectively do trace logging by piggybacking on the existing logging systems. This is a great way to stay on the path for developing new code, right? It may or may not be useful with existing products. It's an easy first step when you're trying to narrow down a problem's scope. And remember, I talked about eliminating sections of code. Well, perhaps with trace logging, as you're logging, I'm at point A, I'm at point B, I'm at point C. And if you know that you never get to point D because things fail, then you could probably eliminate the stuff that comes after point D. However, one of the problems with trace logging is it adds runtime overhead. And this can be a problem with non-deterministic issues, right? That runtime overhead could be just enough to cause the race conditions to not occur. So if you add logging and your problem goes away, well, your problem is probably bigger than you think it is. So learn how to use debugging and analysis tools. And through the many years that I've been a programmer, it really surprises me the amount of resistance that other programmers that I've worked with have to doing things like just using the debugger, right? The one tool in their toolkit is trace logging, right? They don't learn to use other tools. And my advice to you all is learn to use all of the tools I'm about to list, and when they're useful, and as you gain experience, you'll know which tool to use in which situation. So use your compiler. Your compiler is incredibly useful. It knows much more about your code than you do. And it will tell you about bad things in the form of warnings. Read the warnings, pay attention to them, listen to them. They're usually indicative there's a problem here, right? Along the same lines, you have static code analysis tools like CppCon or Coverity, which can provide even more extensive warnings and even suggestions that can help you track down problems in a static sense, right? By analyzing the code at rest without it running. And then, of course, you have interactive debuggers, GDB, LLDB, you've got the Visual Studio debugger, you've got the undo debugger. Learn how to use these things and when they work. You have time travel debuggers, which allow you to play backwards and forwards. A GDB will do that in some circumstances. There's RR that comes from the Mozilla project. The undo debuggers, Live Recorder and UDB, I'm told, are very good. I hope to use them someday. I haven't had the opportunity, but my understanding is they're fantastic tools. There are sanitizers, the address sanitizer, thread sanitizer, undefined behavior sanitizer. These are things that you link into your program as you're building it. And they instrument the code. While your code is running, they can detect problems. They can detect memory leaks. They can detect race conditions with threads. They can find places in the code where you're exhibiting undefined behavior. For example, if you've got an array of values and you're forming a pointer that is outside of that array, right? That's undefined behavior. On a lot of platforms it'll work and you'll never have a problem, but some platforms it doesn't. There are dynamic program analyzers, Valgrind. Probably many of you have worked with or used Valgrind or CallGrind or HellGrind. These are things which create, in a sense, a kind of virtual machine that your program runs in. And it will run much more slowly, but they attempt to monitor what your program is doing and can detect problems for you. And then, of course, you have domain-specific tools. You have, well, strace, which is useful on Unixes. If you're doing any sort of network-based programming, there's tools like Wireshark. If you're doing database programming, there are SQL analyzers that come from things like Oracle or other places that allow you to intercept SQL calls and watch what's happening. So these are very powerful tools for deterministic problems. They're not always useful for non-deterministic problems, especially for those tools that add runtime overhead. Like I said, just the act of adding some runtime overhead can cause the race condition, the data race, whatever, to not happen. A very easy thing that you can do is you can enable or add new assertions. And by this, I mean, static assert in your source code, or assert, the assert macro, in the code itself. And an assertion is a facility that it evaluates a predicate at runtime, and it causes some sort of serious error, some huge red flag, if the predicate is false. And it's a great way to check your preconditions, your postconditions, before and after calling a function. It's a great way to verify class invariance while you're executing a member function. Are my preconditions being met? Is my class maintaining its invariance? Are the postconditions being met? You can use asserts to do this. And the nice thing about asserts is usually they do add overhead, but usually it's a very small amount of overhead. And I find them to be one of the most useful techniques for non-deterministic problems. So the whole point of them is they help you verify the expected state of the program. So luckily, these usually have little effect on execution speed, and they're a good tool for both deterministic and non-deterministic defects. They will add some overhead and runtime overhead and code complexity, but usually the price that you pay is pretty small. Another technique you can use, sort of a mental technique, is backtracking. You start where you think the problem is, and if you're not using like a time travel debugger, you're using the debugger in your head, well, you start where you think the problem's occurred and you mentally step backward through the code. You try to understand the program state at each point backwards until you come to the point where you think the failure has occurred. I don't really have much success with this myself, except for the simplest of problems. So it's a good technique that you can use when the problem is simple, the amount of code that you have to search is small, and it's a deterministic problem, right? It's easy to do quickly. It's a nice technique for forming a first guess at what the problem is. It's much less effective with complex problems, or if the amount of code you have to search is large. And it's basically ineffective for non-deterministic problems, I've found. Another very powerful technique for deterministic and non-deterministic programs is the divide and conquer technique, binary search. Pick a section of code, put an assertion or set a breakpoint in the debugger halfway through that section, or approximately halfway, right? If the assertion fires, or the breakpoint is reached with some invalid program state, then the problem's in the first half. Otherwise, it's in the second half, right? You're doing a binary search. And you repeat this problem of halving until you get to a section that reveals the defect, or at least reveals the symptom. So you don't need to use a debugger. You don't need to use asserts. You can also use trace logging to do this. And for deterministic problems that have a large search area, this is very effective. It's a nice way to narrow down the scope of search very quickly. It's not always effective for non-deterministic problems because, as I said, you could have a large distance in time and space when you do this. And here, the distance in space is the important one. If you narrow down code here, it doesn't really help you if the problem is over here. But it's still a very powerful technique. And we probably all do it unconsciously, and all I've done is just slap a label on it. Problem simplification. Well, this is very strongly related to divide and conquer, and this is basically no overhead. This is comment out code, comment out sections of irrelevant code to the extent that you can, and see if you can narrow down where the problem occurs by commenting out the code. The more that you can comment out, the narrower the scope of search becomes. And this is actually a useful technique if you think the bug is in the input data, right? Start stripping out data that doesn't cause the problem until you come to the data that does. So when you combine this with divide and conquer, it's great for debugging crashes in release builds, right? Because there's no overhead that's been added to the release build. All that's happening is there's something that's not running anymore. And my recommendation is, when you're doing this, of course, and perhaps it's only common sense, work backwards. Start with the things that happen last and start eliminating them, and work forwards and work backwards until you get to the part where you think you found the problem. Another powerful technique, especially for non-deterministic problems, is make the problem worse, right? Vary the context in order to evoke the symptoms, make the failures occur more frequently. And sometimes with non-deterministic problems, this is really the only tool to help you find the problem. And I have a long story about debugging an Oracle-related issue that I'll be happy to tell interested people with nothing better to do, but I don't have time for it here. So figuring out how to make the problem worse, this is very helpful first step in finding and understanding the problem. Like I said, it's very useful for non-deterministic problems, especially when the symptoms are infrequent. You can try and be rigorous about this and use the scientific method. Form a hypothesis that's consistent with the observations that you made, and implement tests, write new test cases to try and falsify or refute that hypothesis. And if you can refute the hypothesis that the bug is here, well, then you think the bug is not there. And form a new hypothesis about where the bug is. Implement new tests to try and refute that hypothesis. And repeat this process over and over again until you get to what you think the problem is. It's actually a way of eliminating sections of code where the problem is not. So keep going until you cannot refute your most current hypothesis. Of course, this requires a lot of thought about what you're doing. This is a non-trivial process and it takes a lot of time. So you can apply this to every problem, right? It forces you to really understand what the code is doing and how the program state is evolved. Unfortunately, and it's compatible with all the other methods that you do. But unfortunately, it's very time-consuming. It's especially time-consuming for code bases that you're unfamiliar with. And honestly, you may not just care enough to go through it because it's just too much work. So, looking at it from another perspective, thinking about deterministic problems, advice here, review the logs, add assertions where needed to verify invariance. If possible, when you're using use an interactive debugger, right? Very helpful for deterministic problems. Use the divide and conquer method. Otherwise, add assertions using the divide and conquer method, right? If you can't use a debugger. For undeterministic problems, again, review the logs. That should be, item 0 on your list. Create a debug build and see if the debug build also exhibits the same problems. Sometimes the act of having the debug build that doesn't exhibit the problems that the release build does can tell you something about the issue. So try building a debug build. And that, by the way, is the whole reason for that clone step I mentioned several slides ago. Because when you've cloned the product and you have your you can make a debug build and observe how the program evolves under the debug build. If you have a non-deterministic problem and the problem rears itself in the debug build, consider yourself lucky, right? Your life is much easier. Add assertions to verify invariance. Assertions are a low overhead way of verifying program state is what you think it ought to be. Add assertions. When you do this, add assertions or comment out code using the divide and conquer technique. And a very big gun here, try to make the problem worse. Find some configuration, some data, some thing that you can change in the context that makes the problem worse. And as a last resort, if these things don't work for you, try and use some of the low overhead debugging tools, right? The sanitizers. You can also try doing debug release builds, like with GCC or Clang. You can build -G, -O2. And in fact, I worked at a company where production code was actually shipped, was built -G, -O2. And it was helpful because when we got the core files back, there was usually enough information left that we could eliminate a lot of code. So what is classifying a problem? Well, it's determining the category of a defect, and it can be useful when you're trying to figure out what's my strategy for repair. But I think more importantly is it's information for posterity that you can use when considering preventive actions in the future. And we have things like syntax errors. The C++ compiler catches these and issues errors mostly. And this is probably more of an issue in multi-platform products where you might need different syntax from platform to platform. More often, however, we get syntax warnings which can indicate basic semantic errors. The code is syntactically valid, but it's questionable, right? There could be a problem there. And as I said before, in C++, this compiler issues warnings for these. There could be simple source code errors, in other words, syntactically correct typos that permit you to make successful builds, but they have latent defects in them. And here's a quick example of something stupid I did a few years ago. I was doing some parsing, so I had a line buffer class. I had a function to read line and a function to parse line. And I had a function to parse the file. So I dutifully instantiated my buffer. And I had a while loop where I would read a line and I would parse the line. And the first time I ran this, it failed. Like, what's going on here? Nothing got parsed. No output. Well, that was the problem. Now, this was before GCC diagnosed this problem, right? But this was syntactically correct code, and the compiler had no way of knowing this is not what I really meant. You have implementation errors, which can represent, problems in the algorithms or where the algorithms and the data structures and the workflows are correct, but lower-level data structures are using incorrectly, and they're breaking invariants or pre- or post conditions that the higher-level structures are expecting. You have logic errors, which I think of as being problems in the high-level algorithms or the workflows that they're logically flawed. They are not algorithmically correct. So a lot of times you'll see mostly correct operation, but there'll be failures on corner cases that were failed to be considered before. These are usually indicative of design flaws, and those are usually things that are expensive to fix. Then you have configuration errors, and the Knight Capital thing that I mentioned, where they lost $460 million. That was a configuration error, right? So you have incorrect or invalid binary components that are included in a release build and get shipped out into the world, right? You have successful builds and they appear to work, but out in the real world, they're not actually the right thing. So let's talk about repairing problems. So this, in my mind, is implementing an appropriate set of source code changes, a set that is necessary and sufficient to resolve the problem. In other words, the minimum amount of changes that you need to implement to solve the issue at hand. And you demonstrate that the repair is complete by passing tests. You create new test assets, you update existing test assets, but in my mind, you've not resolved the problem until you have tests that show the problem no longer exists. So try to minimize your changes to the system. Keep your changes small and localized. In terms of source code, minimize changes in source code. And from another perspective, you want to minimize dynamic changes. Minimize the change to the program state at runtime. Sometimes you can make small code changes that vastly change the program state. You should avoid that to the extent you can, because it could be that you don't actually have a good understanding of all of the program state. As I mentioned before, verify your repairs against your test assets. All of your new and updated tests should pass. They should pass on all your builds, on all your platforms. And make sure that all of the other tests which previously passed also passed. Unless, of course, there's a problem with those tests and you should fix them. But basically, new tests should pass. Everything that passed in the past in the past should also pass. I never thought I would utter that sentence. Okay, delivering a fix, right? Delivery is incorporating changes that have repaired the problem into the product so it can go into production. So, practice good version control. Again, I've been surprised over the years how often this advice is not followed. Don't include fixes for more than one problem in one commit. If you've got two problems you need to fix, unless they're actually the same problem, or the code is intertwined so much that you can't do it reasonably in two commits, try to keep the commits for fixing one problem separate from the commits that fix another problem. Don't include extraneous changes. Don't do gold plating. Don't refactor. Don't add new stuff in your commits. Keep fixes and the commits for fixes separate from the commits for enhancements. Make sure that you include your new test assets, the new ones that you've written or the updated ones in your fix commits, right? You want there to be that strong correlation between the change in the code and the asset that you've created that demonstrates the fix. And if you can manage, if your code base is such that you can commit both of those things at the same time, I strongly recommend you do that. When you write your commit comments, don't just say fixed blah blah. Try to provide a little more meaningful information than that. Now, if you're working with some sort of issue tracking system, then I recommend make some comment in your commit that at least will get the user, the reader, back to the issue description in Jira or whatever you're using. And perhaps in that system where you more fully describe what the problem was and how you fixed it. Verify all of your tests again. Double check that all of your updated and new tests pass and continue. Make sure that all the previously passing tests continue to pass. And I'll say this over and over again. Test, 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 keep checking. Even after you've built a release build that you think has got all the right stuff in it, test it again. If something can go wrong, it will go wrong. And it will most likely go wrong just before you're going on vacation or you have something else that you want to do. So the best way to make that problem go away is to test, test, test. When you're delivering the fix, please, please, please create documentation for posterity. Let posterity, the next person that's going to have to look at this code, let them know how the defect was originally noticed. And that, of course, will be part of that information will come from the problem report. Let the posterity know the conditions under which the defect occurred. What was the context? What were the steps necessary to reproduce the problem? I've read countless tickets where there was a problem and the ticket said, the problem is fixed, no description of what was done, no description of how to reproduce the problem. So if this had to be reopened again, whoever's looking at it the second time has to go through all the work that the first person did. Write down what techniques and tools you use to find the defect. And what is the defects category, right? Is it a logical error? Is it implementation error? Was it a version control error? For sure, let posterity know what you think the underlying root cause of that defect was. And let them know if you think there might be some latent defects that were precluded from happening by fixing this defect. And also let them know if you think there might be some latent defects that haven't been fixed yet. You may have noticed something like, well, module C here might have a problem under these conditions. We haven't fixed it yet, we haven't seen it yet, but it could be a problem. You could make a note to that effect, and you could also make a new ticket so somebody looks at that and avoids that problem before it happens. You should document the mistakes that were made in getting to this point as you see it, and what you recommend for future preventive action so this kind of thing doesn't happen again. And of course, if your company process calls for it, conduct any required reviews, if reviews are part of your engineering process. So in summary, practice defensive programming, assume the worst, because it's always going to happen. Employ an appropriate iterative and incremental development process, And I'm going to summarize this a little bit here. Decide what it is that needs to be achieved. And here I'm talking about writing new code. Formulate a plan for that, achieving that thing. Understand the invariants, the requirements, preconditions, postconditions, context, and then design a solution. You don't have to design it down to the nth detail, but design it enough so you can reasonably start implementing it. Implement that solution in small, discrete, testable chunks. Write code that verifies your invariants, checks your pre- and post-conditions, and for complex components, write a self-test. I've written some classes in the past which, of necessity, were complex things. They maintain complex internal state. And so what I would do, I had a self-test member function. And my self-test member function would go and it would iterate through complex data structures with complex relationships between the data to make sure that everything I thought ought to hold actually did hold. Consider employing the principles of test-driven design. Implement your tests in parallel with the solution and employ good configuration management practices. Remember, the idea here is not to become an expert at debugging. The focus should be on getting better at writing code that's mostly free of defects from the outset. Reproduce the problem. If not in the lab, try to reproduce it in the field if you can. Learn to use all of these great tools that we have available to us. You should have many tools in your tool chest, not just one. Try to leave the code better if you can. Try to make the world a nicer place, right? Please, please don't try to refactor your code. Repair only what needs to be repaired. Don't mix repair with refactoring. Thoroughly document your changes and their justifications. Leave breadcrumbs for the next generation that has to look at this code. Test your changes. Make sure your tests pass. If necessary, create new test assets, update existing test assets. Do what you need to do to prove that you fixed the problem. Run existing tests, and if possible, test in the field. Make sure that no new problems have been introduced and all the existing tests pass. Test it in the lab and test it in the field if you can. Test, 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 test. And with that, thank you. Well, I'm a couple of minutes over, but I'll take one or two questions if anybody has any. Yes? Code coverage tools, yes. Yes, very good idea. I will do that. Thank you. The comment was to add code coverage tools. Yes? Right. So the comment is the human factor, that there's often lack of communication or miscommunication between the engineer and the customer. And my comment on that is requirement, right? I worked in medical imaging for a little more than half of my career. And at one point, the company I was working for had a contract with a major medical imaging manufacturer, and we wrote software for them that ran on MRI scanners. And this was my first experience with this, negotiating a requirements document with a customer. And it was incredibly painful, a painful multi-day process. The first time. Subsequent times is not nearly as bad. But it was incredibly valuable that when we had a term foo, we both agreed on what foo was and how we guaranteed to them that foo was implemented and they could check that foo actually worked. I'm a very firm believer in documenting requirements. You remember I said all programs have requirements, implicit or explicit? I'm very strongly in favor of explicit requirements because they aid communication and help mitigate misunderstandings. And so with that, I think I will conclude. Thank you again, everybody.